Okay, I like this paper because it's not worrying so much about what will happen in the future as with model projections of various things, but actually looking at the historical period to see how models are doing and how heat wave hotspots are changing or trending, let's say. And we know in other podcasts I have discussed this that the IPCC class models, which are used for assessment reports, are very good at producing global mean temperature trends, and then everything begins to be less certain after that because it's very difficult to model rainfall compared to temperatures, and temperatures are also typically good at regional scales and not at local scales where heat waves happen and so on. And nonetheless, you should be able to say whether these models are good at capturing regional hotspot trends as far as heat waves are concerned, because that should be kind of a low-hanging fruit for these models. And if they are not doing very well in the historical period, then what does it mean for future projections? And in future projections, we already know that for the decade or two ahead, the uncertainties in model projections are mostly related to model issues, internal variability or natural variability, and then as you go ahead of, jump ahead more than 2 decades, then the scenarios we assume for projections begin to dominate the projection uncertainties. So in that context, this is a paper that makes some good points that I'm going to briefly report to you. Global emergence of regional heat wave hotspots outpaces climate model simulations. So climate model simulations from the past are not keeping up with what nature is doing in terms of regional hot wave hotspots and their evolution or emergence. Multiple recent record-shattering weather events raise questions about the adequacy of climate models to effectively predict and prepare for unprecedented climate impacts on human life, infrastructure, and ecosystems. Here we show that extreme heat in several regions globally is increasing significantly and faster in magnitude than what the state-of-the-art climate models have predicted under present warming, even after accounting for their regional summer background warming. So typically we look at local scale, duration, intensity, and frequency of heat waves and how they are changing because of global warming. And then there is always the issue of attribution, where you want to see if a particular heat wave or trend of heat waves is related to anthropogenic forcing. This gets trickier. Maybe we'll touch on this here a little bit. Across all global land area, models underestimate positive trends exceeding 0.5 degrees C per decade in widening of the upper tail of extreme surface temperature distributions by a factor of 4 compared to reanalysis data, and exhibit a lower fraction of significantly increasing trends overall. If you don't know what reanalysis products are, you can go back and listen to other podcasts of mine, but basically these are models that are integrated by assimilating data into them over historic periods, so you have the best dynamically interpolated continuous data for climate records. Okay, they carry the model biases as well because you are relying on models. To a lesser degree, models also underestimate observed strong trends of contraction of the upper tails in some areas, while moderate trends are well reproduced in a global perspective. So they are having trouble with the tails, but the middle they are doing okay. Our results highlight the need to better understand and model the drivers of extreme heat and to rapidly mitigate greenhouse gas emissions to avoid further harm from unexpected weather events. The Proceedings of the National Academies of Science provides a blurb on significance as described by the authors. I did forget to put the DOI index here. Let me do that in real time. I don't know why I missed it. This paper appeared in Proceedings of the National Academies of Sciences of the US just recently, and where is here it is. the now these everything now has this silly AI that is trying to help, but it's blocking my text. I don't know how I can remove that, but anyway, we are stuck with too much AI now. So let me put that here. La la la. You cannot see it, but just in case you want to stop the video and stare at it and copy it, then there it is. Okay, so that's going to be made bigger here, and I can give it a red color if you want. Okay. Let me just say again that it appeared in PNAS in 2024 November, I think. Okay, anyway, so let's go forward with the significance, which is, in words, what is the work really good for? Heat waves can lead to considerable impacts on social and natural systems. Accurate simulations of the response to warming is important for adaptation to potential climate futures. Here we quantify changes of extreme temperatures worldwide over recent decades. We find an emergence of hotspots where the hottest temperatures are warming significantly faster than more moderate temperatures. In these regions, trends are largely underestimated in climate model simulations. Globally aggregated, we find that models struggle with both ends of the trend distribution, with positive trends being underestimated most, while moderate trends are well reproduced. We'll look at the distribution in a minute. Our findings highlight the need to better understand and model extreme heat and to rapidly mitigate them as well. So obviously we want to worry about future projections, but historical records are a good indicator of how reliable the models are. But also remember that when we do early warnings, they are going to depend on weather forecast models and sub-seasonal to seasonal forecasts, where a lot of decisions are served well by those. And those have to be good at very high resolution, because unlike the CMIP models used for climate assessment, these models can be much higher resolution because they are integrated for shorter periods, and then there are differences between weather forecast and climate forecast. So we'll leave it there. Okay, I have podcasts on that elsewhere. In the global average, this warming, so just jumping ahead, they are looked at trends, and they are saying that in the global average the warming has been accurately predicted by different generations of climate models, because they are good at predicting the trends of global mean temperature trends of anthropogenically forced climate change, which is basically you give it greenhouse gas increases, land use, etc., and they produce the trends as observed, but at global scales and sometimes regional scales. However, an overestimation of mean warming in some of the most recent CMIP-6 models, commonly known as the hot model problem, has sparked discussions about paying closer attention in multi-model contexts to weighing models by their skill in reproducing observed trends. From an extreme weather perspective, the large and unexpected margins by which recent regional scale extremes have broken earlier records have raised questions about the degree to which climate models can provide adequate estimates of relations between global mean temperature changes and regional climate risks. Okay, CMIP has a definition of risk as a multiplication of hazards, vulnerability, exposure, and even response has been added lately. So just a few more words from the introduction. Here we investigate trends in extreme temperatures by focusing on the warming of the extreme tails compared to trends in more moderate percentiles of the yearly temperature distribution for each grid point. The manuscript is structured as follows. I'll skip that part. We'll look at the figure in a minute. We compare the observed trends with those based on a large number of state-of-the-art model experiments from the high-res MIP. So those are higher resolution model intercomparison projects, as opposed to CMIP-6, which are coarser resolution. So they do some things more and better. So but of course they are forced with sea surface temperatures, and they are not coupled ocean atmosphere models, which makes a difference as well. And then the local and global discrepancies are described, we conclude with a discussion of the physical mechanisms, which we will read a little bit. Okay, so here is the first figure looking at daily maximum temperature anomalies during recent record-breaking heat waves and their temporal context. So you're looking at anomalies of daily extremes, so recent record-breaking heat waves on central western US during July 2021, and it jumped out way above everything else in terms of summer maximum regional mean temperature, daily temperature anomaly. And here you are looking at the same thing for northeastern Europe, and you're looking at the Amazon basin. So this seems to have ramped up much more differently than here. Here is a sudden jump in that year, whereas this has been ramping up for a while, and still there is a jump. This is not as large as this here, but you can see this TX anomaly here is 16 degrees, whereas here it's only about 5 degrees. Okay, so, and here it is about 12 to 13 degrees. Of course, background states matter as well, right? So this is for Southern Africa for January 2016. It's their summer. Remember, this is September, October 2023 for Amazon basin, again in the Southern Hemisphere. Okay, so looking at the observed trend in temperatures, upper tail, I'm getting a phone call. I have to pause for a minute. Okay, so other duties call. Anyway, let's continue. So here we are looking at how models are doing in terms of the observed trends for 1958 to 2022, where the observed period is, trends are derived from this European Union's reanalysis product version 5. As I mentioned, those are a blend of models and data, and they are the best we can do in terms of historic periods, and they're identifying few hotspots here over which regional average change in temperature tail width for different regions are looked at. Okay, and the main point is still the same, that the models are not doing well at either end of the tails, either the reductions in hotspots or increases in extreme heat wave hotspots, but they're doing okay in the middle range. So I won't go into the details here. You can read up the paper. It's very nice, and there are some methodological descriptions here, but basically it's showing a global emergence of regional heat wave hotspots, regional trends in extreme heat tail widening estimated by calculating long-term trends in the differences of the yearly 99th percentile of daily maximum temperature Tx and the yearly 87.5th percentile Tx, the median of the upper quartile bounded by the 75th and 100th percentiles at each grid point over 1958 to 2022. Areas where trends in the annual 87.5 fifth percentile of Tx are negative are shown in gray, and so on and so forth. Okay, you get the main point what we read in the abstract. But if you look at the biases in terms of observed trends versus models, you can see this is showing regional trends of extreme temperatures being underestimated in climate model experiments in multiple regions globally. Comparison of observed trends in tail widening, so yearly 99th percentile minus 87.5th percentile with the 49 simulations from coupled and SST forced climate models. You know, there are details on how these modelings are done, but basically just note that if you look at the coupled models versus what you can get from observation-based estimates in trends in the yearly 99th percentile minus yearly 87.5th percentile, then they are way lower than observed in all the regions basically. Okay, even though the range is large, some of them are not even showing any trend. They're basically straddling the zero line, whereas observations from era 5 show clear positive trends. But you have to remember that the multiple data products themselves are different as well, but not they are relatively closer to each other compared to the distance between the models and the observation-based estimates. So models are still wrong, and here you can see that trends are negative for North Africa and Siberia, and again models are underestimating compared to observational estimates. Of course, Arctic is problematic because even observation-based estimates are quite different, but models are mostly in the negative, whereas observations are positive, and so on. Okay, so tail width trend distributions, it's a figure that's a bit complicated, but they look at skewness from high-res models and low-res models, and we will read the message in a minute that high-res models do improve certain things. So you can look at cumulative distributions difference as well, and you are looking at trend in yearly 99th percentile minus yearly 87.5th percentile. So that is how the tail is widening or thickening on both sides, positive and negative. And again, you are looking at the skewness, but main point is better to jump to conclusions and gather the most salient points, because the details are in the paper. Actionable climate assessment for effective climate adaptation and mitigation requires skillful and reliable projections of extreme weather risks under different emissions scenarios on a regional to local level. This holds particularly true for the representation of recently observed extremes of large magnitudes that might be rare under current climatic conditions, but will become more likely under continued greenhouse gas emissions. Skillful projections of trends in such extremes, unprecedented or record-shattering extremes, must build on a thorough physical understanding of why they are emerging and the nonlinear behavior responsible, so that model simulations can be benchmarked with historical periods and potential biases can be accounted for. There are many papers looking at how to do bias corrections even for projections, and then there are papers arguing that that doesn't help, and so on and so forth. But in this context, in large and densely populated areas such as Western Europe and China, and other areas that feature important biomes for the world climate, such as the Amazon and polar regions around Greenland and Canada, some of which have been discussed in the context of climate tipping points, the multi-model mean of climate simulations of the past decades does not show the enhanced warming of the temperature distributions upper tails observed in these regions. Note that for the Amazon, the strongest trends have emerged over the last 23 years and are found for ERA 5 only, which means it's not there in the other observational products. So here, let's see, do we have yeah, we don't have the Amazon here. So anyway, often the multimodal mean is used and prioritized in many assessments of climate risks, while upper percentiles are treated as implausible scenarios and are at times rejected as outliers. For instance, the 1.5 degrees C warming target established by the Paris Agreement was set largely based on avoiding dangerous climate change, in part associated with critical tipping elements and or thresholds in the Earth system. A lot of words there, but dangerous climate change is not very well defined, and tipping elements or thresholds are there in the system, but it's not always easy to predict them or say very confidently where they are going, especially in the context of such biases that we looked at. However, if impacts of global warming, such as amplified extreme heat, proceed faster than expected based on the multimodal mean projections used to support such a warming target, its utility may deserve reconsideration. We find that in numerous regions, trends in the tail widening of extreme heat distribution over the past 65 years exceed the 95th percentile of the model spread, and in some cases even exceed the spread entirely. Trends shown in ERA 5 reanalysis are outside the modeled range for southern South Africa and Arabian Peninsula and the Arctic Canada, which are all experiencing rapid warming. And this is irrespective of any model configuration investigated here, while the observed uncertainty intervals determined by bootstrapping overlap with the model spread. These findings hold for model simulations at higher resolution or forced with historical SSTs as well as with greatly expanded ensemble sizes. Okay, few more words. Just jumping ahead in terms of attribution. However, disentangling the relative importance of externally forced or related to greenhouse gas increases and internal variability in the observed trends may be key to attributing the sources of model observation discrepancies. So in the real world, you have El Nino, La Nina, PDO, AMO, all sorts of internal variabilities which don't match exactly those renditions, or the year when an El Nino happens in the real world is not necessarily captured by a CMIP6 model, because that's not a prediction model. It's just integrating freely and mostly focused on how the temperatures are warming, especially at global mean levels, because of increased greenhouse gases and solar forcing volcanoes and land use change and so on and so forth. So it's a detail that you can listen to in my IPCC podcasts. Coordinated single forcing large ensemble experiments such as the new large ensemble single forcing model in comparison project might help in improving our understanding in the relative role of various external or internal drivers in extreme event trends. So again, details. Ensembles is where you say Mother Nature is going to go somewhere, but she could have gone in 10 different directions, but the models, when they integrate forward, they have to see where all Mother Nature could go, because that's the best we can do. So we do many perturbations in the beginning of the integration and produce plumes or ensembles, and it could be multiple realizations of the same model or multiple models with multiple realizations. The larger the number of model realizations you have, that's what is called large ensemble, the more likely that you will capture the internal variability that's possible in the real world and what the models are capturing. Okay, so jumping again ahead further, machine learning approaches have shown promising results for providing more reliable bias adjustment of climate model output. These are based on methods from image processing and are better in retaining the relationships between variables compared to more traditional quantile mapping approaches. This is particularly important when analyzing risks and impacts from compound extremes. ML techniques could also assist in detecting nonlinear and regime-changing behavior in the ocean, atmosphere, land, vegetation system, or the Earth system, and provide causality where common drivers experience strong couplings and feedbacks. System means there are components and there are feedbacks, so this can amplify or damp initial perturbations, right? Beyond using ML for analysis, recent advances in ML-driven weather forecasts exemplify its potential in climate modeling. In addition, ML might offer accurate and less computationally costly simulations for resolving important sub-grid scale processes compared to purely numerical frameworks. Again, a lot of technical words, but basically models have a resolution, a grid size in longitude and latitude, vertical into the ocean and so on, which are tens of kilometers, but things happen at a much smaller scale, and the processes that happen at a much smaller scale are not represented explicitly, so we parameterize them and call them subgrid scale processes. And there are many papers, and I have podcasts on how AI is being used to capture those processes from data and put them into the model, or sometimes merge numerical models with mixed machine learning models and so on. So ML approaches, however, must be combined with others that can physically explain and understand the causal flow identified by ML. New assimilation techniques that integrate observational datasets and exploit advanced interpolation frameworks have been proven to improve the depiction of extremes compared to reanalysis datasets and provide climate information at a higher resolution. While our findings provide many avenues for interesting and relevant new research, the authors stress that the best way to reduce both uncertainty in and exposure to climate impacts is a rapid transition of relevant societal sectors away from fossil fuels to stabilize temperature rise. Okay, so it's a nice caveat that things are happening which we can infer from reanalysis products, but models are reproducing some things very well, like the global mean trends, but regionally they are producing mid-level trends well, but the tails, both at the negative and positive ends are not being captured very well, and this is something to keep in mind as we look at future projections and try to make adaptation and mitigation plans. Mitigation has to happen. Global issue, global leadership, all countries are participating. India is doing well, for example, but adaptation, dealing with hazards like heat waves are very hyperlocal, local issues which require more information, more reliable information, because you cannot put money into adapting to climate change everywhere. There may be some no regret, low cost solutions like greening, urban green cover and so on, but to do more than that, to build shelters, hydration centers and so on, you need much more reliable hyperlocal information. So it becomes critical to make sure that we are capturing the trends properly. Okay, so I will leave that here. I'm obviously brief as usual, but you can go and read the paper to get more details on the modeling, the analysis and so on. Okay, see you in the next topic.